First of all, it's truly an honor to be here in this wonderful ERI summit. I want to really congratulate DARPA, Dr. McCant, for organizing such a wonderful conference. I want to also say that we at IBM are very proud to be partnering with DARPA in many important and groundbreaking projects like introduction of SIGI technology or introduction of SOI technology. These came out because of the partnership with DARPA. So we are very proud that that DARPA pushes the limit. They always pick the most difficult problem in the industry. And this is something like what IBM does as well. So today I'll talk about the topic of the day, AI, and how, what IBM is doing in this space. And we look forward to putting some challenge in front of all of you and working together with DARPA to develop more energy efficient and cost efficient AI technology. So with that, let me start by just to kind of calibrating everyone on the entire life cycle of AI. Just a very simple steps, because sometimes it's not clear which part of AI life cycle we are talking about. So if you look at the large model, or they are called the foundation models, which are the base or the backbone of generative AI technology, it has, broadly speaking, 4 steps. Step 1 is the data preparation, where you want to make sure that your data is clean, it's legal, and it's something that you can actually use to build the model. Second part is the distributed training and model validation. That's the really energy-consuming, very expensive, and very long process of building these large foundation models. However, after that is the 2 steps which are very important, which is model adoption. Because the whole idea of foundation model is that you build this foundation model, and then depending on the domain and the space where you want to operate, you can adopt this model based on less amount of data. And that's the power of this foundation model. And that's the power here when you are trying to be in an uncertain environment, in an edge environment. You can start to live with less data, but still achieve superhuman level of accuracy. And finally, inference. How do you deploy these models? These models are huge. As you've seen from the graph below, these number of parameters on these models are growing almost exponentially. Models of the size of 500 billion parameter model. These are very powerful models. However, how do you compress this model? How do you make this model useful for more energy constrained, more data constrained edge environment? So I'll talk about this, especially the later part, the model adoption and inference aspect of the generative AI lifecycle. To give you a little bit of a background of IBM and IBM research, IBM research, as you can see on the left-hand side, has been around for more than 75 years. And we are very proud to be always working on technology of very high interest to the society. These days, as you can see, we have 19 locations worldwide, of which the locations identified in pink are the locations where we drive AI hardware technology. And on the right-hand side is our AI hardware research center, which is located in Albany Nanotech. Albany Nanotech, where IBM works, is the only of its kind public-private partnership, which is really pushing the limits of semiconductor technology, and these days, especially in the domain of AI hardware. So in this journey of AI hardware, we put a challenge to ourselves. We launched AI Hardware Center in 2019 with a challenge of, can we reduce energy efficiency or improve energy efficiency by 1,000 times in 10 years? Because if you look at all the things we talked about earlier on, the one thing we all know is that AI is just energy-consuming technology. It's a completely, the data centers are consuming megawatts of power to build these models, and then you have to deploy these models. So we went on a journey of, okay, what kind of innovation we can introduce with all our partners in this journey to make AI hardware technology much more sustainable, much more cost-effective as well. So we looked at it from today I'll talk about 3 topics here. That said, IBM is uniquely positioned where we look at full stack. We have very strong semiconductor research team, but we also have very strong algorithm team as well as application team. So we look at end-to-end, all the way from deployment or application to how do you convert those applications to the right model, then convert that into the right arithmetic, and then translate that into the right semiconductor technology, and go back so that this entire cycle has to come together in a more energy efficient and cost efficient environment. So 3 aspects. First is to look at the arithmetic itself. How can we use reduced precision arithmetic and convert that into the right models or compressed models, and then put it on the right processors or accelerator to gain significant energy advantage. Second aspect, which is a big part of today's this ERI, is the heterogeneous integration environment. This is the technology of future. That's where all of the innovation will come together. And what is our role in that, what journey we are on, and what this community today here is working towards in creating this broader ecosystem so all of us can participate in that. And finally, just as I started in the beginning, we always look at what's next. In this case, we are looking at analog computing. It's a little bit out there. However, that can have advantages of hundreds of times improvement in compute efficiency, because now you don't have to move data between memory and compute all the time. You can do in-memory computing, focusing on material innovation. So on that journey, IBM research has always been, we are very, I'll say, fundamental or science-driven organization. We started from, okay, let's start to look at it from the first principles. What is the arithmetic involved in this deep learning computation? And as you can see on the left side, we were the first one to publish papers on using less number of bits or reduced precision computing to still be able to achieve same level of accuracy. And we've been on this journey both on the side of training as well as on the side of inference. As you can see, most recently, we were able to demonstrate that one can achieve same level of accuracy with less number of bits or with reduced precision, going as low as 4-bit for training and as low as 2 bits for inference. However, these are not easy tasks. It needs all of you, the community, to work together. And how do you exploit this capability? And then especially on the side of algorithm, how do you further advance the weight quantization and sparsity, these type of technologies, so that you can start to use less number of bits? And then at the end of the day, the neural network itself is changing and evolving. And how do you keep up with the evolving neural network so that you can subsequently, again, apply the right quantization, sparsity, et cetera, technology, so that you can come back and use less number of bits and still get the same level of accuracy? In that journey, we built our own accelerator. We call it IBM Research AIU. It's built in 5-nanometer technology, which is essentially optimized for generative AI workload. It's of course enabled using Red Hat software stack, and we are able to demonstrate both inference and training as low as int 4 and int 2 level. So that's the journey we are on in this part. Now, very recently, we published a paper where we are exploring the promise of reduced precision in the transformer model domain, where we are developing new quantization and sparsity technology for fine-tuning. Especially, that's an area that is of high interest. And we are able to compress pre-trained transformer models to 4-bit. And that combined with 50% sparsity, we are able to demonstrate 16x compression while maintaining model accuracy. And these are for transformer-grade models, which you can imagine, if your model is compressed that much, that provides you so much opportunity when you deploy these very complex model in an energy-constrained edge environment. The challenge for the team here, working with DARPA, is that these models are constantly evolving. And how do we collectively, as a community, keep up with evolving model demands, especially towards fine-tuning and inference, which is what is needed in an edge environment? Now, looking further beyond that, come back from the chip architecture to the technology itself. We know that the technology which is really going to create differentiation is the chiplet technology. And I started on the left side. This is the roadmap that IBM Research has put together on the digital side, which is, okay, start with the better architecture, work towards model optimization and compression of those models using the technology I talked about, then start to put them all together in a much more disaggregated environment, and eventually go towards the 3D stacked memory and chiplet technology. Now, these are good and easy to be shown on a piece of paper. However, these are very challenging problems, especially for a broader community. A few large companies can do it because they can have proprietary standards. However, we really lack standards to build and deploy system utilizing chiplets. So I'm very pleased to see that DARPA program is driving to create the community and create these standards so that we can all participate and work together. And also in this case, we need to really focus on both software and hardware co-optimization. Hardware alone is of very little use if we cannot look at it comprehensively in a system-level environment. In that journey, now we have to transition from the way we used to do DTCO or design technology co-optimization to a system technology co-optimization, where you look at system-level performance, then you develop your chiplet technology, what type of ground rules you need to have, what type of IP blocks that you need to put together the entire system, and look at metrics like system-level performance, power, area, cost, thermal, mechanical, many more system-level requirement. Again, there are many challenges in this journey. This is the way we want to do it. However, there are many challenges. What are the right technology definition? Do we have a robust design environment, EDA environment, so that a 3D chiplet design kit that can be made available for broader community to use as well? Also, first time right, because now you're using chiplet from various sources, and the risk to your system level optimization is very high. And then you want to be able to launch this product in time. So many challenges that we need to work together in this domain as well. Finally, going beyond chiplet technology is the long-term effort that we are driving in the space of analog in-memory computing. Now, this is a very exciting area. Obviously, we all know that our brain doesn't think, if we are trying to use AI technology, we don't think in the digital domain, we think in analog domain. So how can we learn, and how much we can learn from the analog computing, so that the core functions like MAC functions can be performed in memory? And that comes to, again, the area where DARPA specializes is to focus on fundamentals, take on very difficult problem in the industry. This is an area which is essentially focus on material innovations. On the left-hand side, we develop the synaptic element in this case, which is using PCM or phase change memory. As you can see on the left in the two pictures, one is programmed, another is not programmed, and you can see how the crystallinity of that material changes. That changes the resistance, and you can store different amount of weight at that synaptic element. And on the right-hand side, this is the first time ever in the industry where we were able to show full integration of full chip using analog memory computing, in this case, essentially using PCM as the element to be able to store different weight, and being able to develop algorithm which is aware of the chip design itself. It's fully integrated in 14 nanometer technology. We build this end-to-end in our Albany Nanotech facility to be able to now push the limits beyond digital world and beyond chiplet world into the true analog world. And especially in the digital world, as we are learning how to quantize and how to build models at 2-bit precision, we are starting to get closer to analog level of precision itself. So we are learning from digital and applying that into the analog domain here. Finally, you can see that this is a very recent paper that we are very proud that we published at Nature Electronics, where we are, for the first time, we are able to develop hardware-aware training, which is a family of innovative training algorithm that compensates for NVM, in this case, phase change memory material non-idealities. Where on the left-hand side, you can see the network topology. And we were able to be able to map this network topology on different tiles on the hardware. On the left-hand side, this is an analog mixed signal chip demonstration, because again, the world is digital. So as we are developing this analog AI technology, we need to be able to figure out how do we combine digital and analog in this case, so that we can communicate with the rest of the world, but still enjoy the benefit of analog AI technology. We are able to demonstrate image classification tasks involving millions of synaptic weights, some of the standard models like ResNet 9, C410. These networks were mapped on the PCM tile, and this is and we are starting to get the accuracy, which is very close to the floating point 32-bit type of accuracy that you will get if you do it traditionally using the digital technology. So this is the journey that we are on. We are very excited again to be working with DARPA and with all of you in creating more energy efficient and cost efficient AI hardware technology for the future microsystem, which needs essentially a community that works together around all three axes, axis of algorithm and software, which is extremely important. That is what defines how we build the chip and chiplet technology, and then combine that with the system, because at the end, what we are looking for is the system level optimization for this AI workload that we want to deploy in an uncertain edge environment. Thank you very much for your attention.